Just hold on a second, I will pop up the Jamboard. Okay, so I think it's visible to all of you.
Yes, sir.
So today we are going to start this whole topic on systematic evaluation and validation. So till now you have learned about training a neural network. So essentially what happens is you designed a neural network, you trained a neural network, and with the trained neural network, you can do an inference. So in the overall pipeline of this process, what it's going to be, you will have a data set. This is the training data set. Then you have some listing, which is the problem statement. Or sometimes also called as software requirement specification. So if you're actually doing a commercial project, then it would be called as software requirement specification or requirement specification, SRS as it goes. And you will also be given down some data on which you will have to work it out. So then here comes the designer. And the designer's job is to give a sample neural network. Okay. So the problem statement goes to the designer, you give a sample neural network. Then what do? You use this data, which also feeds into the neural network, and then you run a training exercise. So after you have trained, you have a trained model of this neural network available over here, and you can now deploy this one. So this goes on to deployment. So deployment as in like you have a website where this thing essentially sits, and then given an apple, it will say that apple. Something of this sort. This is what is going to happen over there. Now the point is that if this whole thing can happen, the question is that how do you really look at it? That when it actually gets into this production environment, that it works out good. There is a bigger question to answer over here. Okay. So now, if that is the scenario, then it works something like this. So that's what we would get into. What this thing is, what we call a systematic evaluation. Okay. Now broadly, based on ML tasks, let's not call this machine learning. Let's just call it as deep learning tasks. So you can divide this whole training into two broad categories. One of them is supervised. Another is unsupervised. And the question is, what are they? Supervised learning can be defined as where you want to find an objective, where you want to create a model, say H is the model, which takes in X and is trained using a set of data of X and Y called as X and Y train, and then produces an output Y. And in this whole process, so this is my model. And in the whole process, it does it by minimizing the loss between Y and Y hat or Y prediction. This is my objective. And this is my loss. This is what I know about supervised learning. In case of unsupervised learning, you get something like this. You have a predicted value of Y based on X and only X available in the training data. You don't have any class labels available to you during training. And what you do over here is that you try to maximize the loss between your predicted Y and the whole set of Y without the predicted Y. So all set of Y minus Y, something of this sort. So this is still the DNN model. This is your training objective. And this is loss. This is what we know about DL tasks in terms of supervised and unsupervised learning. So next comes down a very critical thing, which is called a sampling issue. Okay. Now the point is, how can different kinds of sampling arise over here? So one of the issues is when your sampling is highly biased. So say in this kind of a scenario, this is one where it is a biased sampling problem. So if I essentially want to say learn by decision boundary, so my decision boundary can either be this one, or it can be this one, or it can be this one. So essentially there is a lot of confusion on the decision boundary. And not just that confusion, along with that, my model. So this is 1, this is 2. My model is influenced by the majority class. There's another major problem which I would be facing over here. Okay. Now the next one is which is unbiased, but then it has low variance. So technically what happens is that okay, in a low variance scenario, so you still have the same number of samples over here, but the point is, although like the bias is not there, so it is not influenced by any of these, any one of the classes. It can give you a similar thing, but you still have lot of uncertainty on the best decision boundary. That uncertainty anyway still remains over there. And then you have this one, which is called as unbiased and high variance. So an unbiased and high variance scenario is where your classes, your data is provided in such a way that this particular boundary which you get down in the decision, there is only one unique possible combination, and this is something which is the most preferred. So this scenario is most preferred. However, that's barely within your prerogative and option that you might end up coming to this kind of a scenario. I mean, though you definitely prefer that you have that kind of a scenario, but there is no way you can guarantee that you will always have that kind of a scenario. That's the best of the world. But however, you can always resample the data and then come to. So essentially what I'm saying is that for any class where you see that so one is like it needs to be it needs to have a high variance. You cannot really play around anything with the variance, but you can definitely play around the biasness. So maybe it has a very high variance, but then the data is biased. So one of the classes has more number of samples, significantly more number of samples than the other classes. So what you have to do is you will have to either either oversample the class with lesser number of samples, or you will have to undersample the class with more number of samples. That's something which you will have to definitely do over here. Now comes the next part. So this is where we have understood in terms of like what are the basic definitions of an understanding of the data and the problem. So Let's go over here. So as I did say that what you have is so what you initially start with is a data set and a software requirement specification, which comes to the designer. Now, as a designer, from your software requirement specification, the first thing what you need to find out is what is the task of this deep learning, whether it's a supervised task or an unsupervised task. Based on that, you will have to create your appropriate model, understand what should be in your training data, and then create the loss which you require in order to do it. So once you understand it's supervised, you know what should be the loss function to be used. Once you understand it's an unsupervised problem, you will have another set of loss functions to be used over there. Now, once you know that, the next part comes down is look through the data and understand whether it belongs to the biased category, unbiased and low variance category, or unbiased and high variance category. Now, this is something which is preferred. If you have this category of data, then you don't need to worry at all. But in general, you might not end up having that one. So if you have say this category of data, then you really cannot work out. You still have to live with the uncertainty. This category of data, but with a high variance. Say you have biased data, but with a high variance. In that case, you can undersample the highly represented class and come down to this equal biased or an unbiased representation, or oversample the underrepresented class and come down to this unbiased representation. So now, after this comes down the systematic evaluation part. So in systematic evaluation, what we start by doing is what is called as folded cross validation. Okay. So first and foremost is to understand what is folding. So what this will do is, so essentially you need to create a set of such small, say sample set. So what you do is you have your original data set. So now from this data set, you split it into K subsets. So what you can do is that you will have small subsets. This is S1, S2, S3, like this up to Sk. Okay, such that and say this is S, such that some Si intersection Sj is a null set, which essentially means that there is no overlap between the subsets, no element wise overlap, and union of all Si's is equal to S. So which essentially means equal to 1 up to K. Essentially means that it has been equally divided into all of them. Now, along with that, what you will have to do is that say that within this one, so it's say like n of small omega is the number of samples per class. And now if each of these uh, beans, each of these subsets will have to be made down to be of a form where the equal proportion between the classes of both the samples, then the number of samples in S1 or any of them is going to be NW divided by K number of samples per class each of the subsets. This is what it is going to be. Okay. Now, if I can make this one, there will be an interesting thing which will now start occurring. So what you can do is, so this is where the folding comes from. So what folding does is, you can define a fold, say a fold I. In this, you will have a training set. So training set is this whole set minus Si is the training set. So what do you do? So this is essentially union of all Sj for I not equal to j. This is essentially what it consists of. Okay. So the number of samples per class in training set is equal to n omega divided by k into k minus 1. This is the number of samples from a given class, which will come down over here. Now the test set is what will consist of Si. So ith fold will have Si as my test set, and all the remaining subsets over there will be grouped together, and that will form the training set given. Now what I can do essentially is, since I have k number of such, so in a k fold experiment, what you do is, so in the fold I, train this model H with I will call this S train I, validate with Si. Okay, and then repeat over all I equal to 1, 2, like this up to k. So keep on repeating this over and over again. And as you have this one repeated, so I mean, this will complete its whole process over here. Okay, so that's the whole aspect of doing a k-fold cross validation. So is this clear till here?
Yes, sir. Yes, sir.
Looking at the grim response, I doubt if you have understood anything of what I am doing today. Rest of the class, are you there in the class, or are you just logged into MS Teams and sleeping?
Yeah, yes, sir.
Yes, sir. Yes, sir. Understood.
Yes, sir.
Yes, sir. Understood, sir.
अच्छे से yes sir बोलो. Next week there is exam. All the yes sirs will become very evident when you get the question paper.
Sir, I have a question, sir. Sir, actually, I just want to know, like, when the the uncertainty of all the classes are high. Like in the case of, for example, I wanted to classify a satellite data, where I have a few classes where the uncertainty of all classes are very high. So, what sorts of sampling strategy we can use in such cases? Because we have almost all the classes where the variability is large. So what kind of optimum number of samples should I select to?
Okay, so now I have two questions.
Hello,
what is your definition of uncertainty?
Uncertainty in the sense that, for example, in a simple case, for example, from a satellite data, I want to classify trees, for example.
Okay.
Where if I see for example, from a high resolution image, the variability of in terms of shape and other properties are very high. So I cannot have a good number of representations from my data, so that I can develop a generic model so that all sorts of different trees can be classified. I mean, as an example, I'm telling. So
Okay.
what sorts of sampling I should use in such cases?
Just hold on. So actually, you have a very good scenario. You are speaking about a scenario where you have a high variance case.
Yes,
So
exactly.
variance means that the variability of appearances of objects in a class, or all the features which I can get for objects in a class, is very high, which is actually a very good condition, because then you know what is that whole spectrum of diversity over which your data can occur. That is not a bad thing. That is actually a good thing, where you need to stop thinking in terms of a classical designer. So you can either solve these problems by making your own rules and like engineering your own features, then making your own decision rules, and then coming to an output. You can do that. In order to do that, you would want that everything looks almost similar to each other, so that with human reasoning, but everything may not look similar to each other. There might be a good amount of variability across each of them. So the point is that if things are varying in nature, you don't have a control over how things vary in nature, how the data comes to you. If that has a high, it exhibits a high variance, which is what you know about it from pre-existing knowledge, and your data also shows, your data set also has a similar amount of high variance, then it's a good thing. So preserve all the data. Why do you want to throw it off? Like sampling is something which is not guided by variance. You cannot do anything with the variance part of it. But sampling is something which is guided by whether it's biased or unbiased. So this is one part of my understanding. When you are saying that you have a lot of uncertainty, what I understand is that you are specifically indicating variance over there. Now, what's the next problem which you?
No. My question is the same thing only, because, for example, I have a an image, and I collected say some 1,000 training samples. So those 1,000 training samples, how do it represent the overall variability of all different sorts of trees in that image, so that when I develop when I do inferencing, it should classify all different types of trees, for example, from that image.
Yeah. So essentially, if it's a supervised classification problem, you need a
Supervised
subject
classification. Yeah.
You need a subject matter expert to come down and label your samples. So your data set has to be created such that it consists of labels. Where is that one? Yeah. If you're doing a supervised problem, then you need to have this labeled samples coming down over here, and these labels and which samples to take, they will have to come down from a domain.
Yeah, even when a domain experts cannot precisely tell you that which are all the samples you need to consider. I mean, what are the optimum solutions in such? Yeah.
Okay, so 2 points over here. Then the domain expert is actually not an expert, but a domain novice. This is my understanding, since I work very closely with say domain experts from a different setting, clinicians, essentially radiologists and pathologists. So I have dealt with the whole spectrum of people. Some of them claiming to be domain expert, but they are full of doubts. They cannot make a decision, and then there are other people who can really correlate several other factors, and then say, okay, this is what it should be because of these other conditions which also indicate a similar thing. So that's one part of it. But the other part is that yes, domain experts can also be suffering from uncertainty, because if you want them to label a data, so typically our method is like when we want to label a data, we don't label it based on only whatever is seen in that data. We actually take a lot of other factors into consideration. See, even in healthcare problems, when we do it, I might be labeling a radiology image, but then I have all the other things like physically palpate, like if you palpate certain parts of the body, then what is the nature of that one? What are other lab test reports? So if there were some biochemical tests, etc., which were done, whether the person has fever or not, height, weight gain, weight loss, blood pressure levels, everything is taken into consideration, and taking all of these things into consideration, then these labels are essentially generated over there. So that's how we look into it. So this is a very critical part which we need to understand that labeling is not done just by looking at that data, then it will not really come to a solution, a feasible solution as such.
Sir, I
Now,
have a question. So in the second slide, in the second slide for the unsupervised learning loss function, so in the unsupervised dataset we don't have any y labels. So what do you mean exactly by the entire y data?
so entire Y means that on the whole data set, you are predicting out some different groups over there. Okay, some groups of Y which comes out. And now say it's something like this, that I give you the data and I say, okay, let us see if this belongs to entire set of Y is basically 1, and what I'm saying is that some of these samples will come to the first class level, some of them will go to the second class level. So what I want to do is, in order to do them into these two groups, my objective is to maximize the distance between the two groups.
Okay, sir. Okay. Yeah, intra-cluster distance. It's okay. Okay, I got it.
Sir, what about data processing, pre-processing?
So, I mean, sometimes we do these normalization and everything. I will come on a case-to-case basis over there, like when it is needed that you basically normalize out the data so that there is not much of diversity which comes in. Yes, we do it, not majorly, but yeah, sometimes we do end up doing it.
Sir, if we don't do it, does it affect our result, or does it depend on our data sets?
Okay, now let me give this example. So say images can be represented as 8-bit images. The other side of it is it can be represented in floating point values, but between -1 and +1. Now, in these cases, what happens is, in the case of range limiting to -1 and +1, generally your mean can be made down to be 0. So that would become a zero mean system. In the second case, the mean will not be 0, but it will be what we call as range normalized. So everything is always between -1 and +1. Between 0 and 1. And in the other case, it's a normalized image. It's a full range image over there. Now, say that you trained a network to take in images between 0 to 255, and next from a camera you get down images which are between 0 to 5,000 or 0 to 10,000, then that will not work out. So in general, most of these models, what they do is that they essentially do a zero mean unity variance of a system on the data, which means that you subtract the mean from the data and then divide it by its variance. So that would make it a whitening transformed out data. And that data is typically zero mean and has a variance of 1. So it does not necessarily mean that it will always lie between -1 and +1, but in general, the variance is 1 over there. Now, for that kind of a data, and when you train these neural networks, what you need to do is you can very easily deploy this neural network to another scenario where the only thing you have to do is you can be given any data coming from any source. And because you know what kind of a transformation has to be done on that, you just need to transform that data, and that solves all the problem.
Sir, but I was recently I was seeing some medical images this feed processing. So we have to do in enhancement or green channel enhancement, red channel enhancement, or like extraction actually, and other things also.
I believe that the person who was trying to do that, at least for a deep learning problem, did not understand anything about deep learning, and so they were doing it. In general, for medical images, we don't do any of those post-processing in terms of enhancing something. The reason why you don't want to enhance
green channel extraction actually, I'm saying.
What?
On a retina blood cell images, blood.
Okay, so for retinal images, yeah, I do have this observation that traditionally people used to do a green channel extraction, which is the reason for that is that because there is blood flowing within our eyes and you will have oxygenated and deoxygenated blood. So the best contrast which you get down, so either blood is red or it's blue. So the best contrast to get down blood vessels is to see the green channel, because you are subtracting out both the blue component and the red component from that one. So that's how you get down the best contrast coming into it. But in general, I do not support that whole way of working out, because essentially that's the beauty of deep learning. You don't have to condition your data too much. The only thing what you need to do is do a what do you say, a whitening transform. So subtract the mean and divide by the variance, so you get a zero mean unity variance system, and that should be enough to run it out. You don't need to run only on one channel. Why do I really want to do that? I can input all the three channels and run a full conditioning network on top of it. So we don't do it. That's my part of it. Other than there might be cases where there is a compute issue or a space issue, then we might have to relook into it. But the general thing is that we don't do it. Okay. Now there is just a quick thing around it before I close it out. So let me just finish. We are almost at the top of the hour. So there are certain metrics for evaluation. So these are called as standardized evaluation metrics. So what happens in standardized evaluation metric is something like this. You have a prediction and you have the ground truth. So you have positive class and negative class. You can predict out similarly as positive class and negative class. And we need to look into what these are. So if a positive class is predicted as positive class, it's called as true positive. If a positive class is predicted as negative, then it is called as false negative. If a negative class is predicted as positive, then it's called as a false positive, and a negative class which is actually predicted as negative is called as a true negative. Now, based on this, there are certain metrics which are defined. One of them is accuracy, which is equal to TP plus TN divided by the sum of all samples which go into this experiment. Now, the next one is what is called as sensitivity, which is equal to the ratio of true positive to all the positives in ground truth. This one. Then comes down another thing which is called as specificity, which is defined as true negatives divided by the sum of all negatives over there. Then comes down precision, which is defined as true positive divided by the sum of all the predicted positives. Okay, and then you have something which is called as F-score. So typically, which is what is recommended for most of these classification problems to be reported in, and it works out pretty well when you have biased data. In all the other cases, you would see that for biased data, this will get severely influenced to the performance of the majority class, but F-score does not actually get influenced towards the performance of the majority class. So these are metrics which are typically used when trying to report out any kind of a classification problem, and there are interesting avenues around it. So I will come to that in tomorrow's discussion, where I will take this example of sensitivity specificity and draw something which is called as receiver operating characteristics, and then show you how a variation in those attributes actually impact it significantly. Okay, so that's all I had for the day, and tomorrow we again get back, and then I will start with the ROC curve and then show you how these things, how a change in these things actually makes some impact.